Hey there, Mr. Sutton here, bringing you the Pre-Cal Honors Chapter 3, Quiz 2 Review Solutions on Rational Graphs and Inequalities. Before I go ahead and find all the intercepts, holes, and asymptotes and try to graph this function, I'm going to go ahead and factor it because there's some things I need to know in order to get all that other stuff. So taking a look at my numerator, I need numbers that multiply to negative 30 and add up to 1. That would be, let me think, negative 5 and positive 6, so x minus 5, x plus 6. In the denominator, I'm looking for numbers that multiply to 10 and add up to negative 7. So negative 2 and negative 5 would help me down there. X minus 2, x minus 5. And I see very quickly that these x minus 5s can cancel if I want, leaving me with the simplified function of x plus 6 over x minus 2, which I'm going to need for quite a few things down here. So let's go ahead now and find the different intercepts, holes, and asymptotes, and then we'll graph this. For intercepts, I'll start with the x-intercepts. Those are going to be x values that zero out the simplified numerator up here of x plus 6. So if I set that equal to 0 and solve, I have negative 7 for my x-intercept, or negative 6 rather. And then for y-intercepts, I have to plug in 0 to the original function. So if I do that, everything conveniently zeroes out except for a negative 30 and a 10, which I can reduce to negative 3. All right, let's go ahead now and find some asymptotes. Vertical asymptote, that's going to be x values that zero out the simplified function. So that's going to be x minus 2 equals 0, so x equals 2 is our vertical asymptote. For holes, those will be x values that would zero out, make undefined the original equation, but not the simplified one. So we're looking for factors that got canceled out that would have given us 0 in the denominator if we had not canceled them out, like this x minus 5. If I set x minus 5 equal to 0 and solve, I have x equals 5 as the location of a hole. Now let's also think about horizontal asymptotes. Since my degrees x squared and x squared, second power, are the same for the numerator and denominator, that means I take the ratio of the lead coefficients, so the numbers next to the x squareds, which are both invisible ones, I take the ratio of those, so the division of those, and that's going to be my asymptote. So I have y equals 1 over 1, which is just 1. So we're going to go ahead and graph what we've got, and we'll see if we have enough information to keep going. We may need to get some additional points, but it's hard to tell until we actually put all this on there and see what falls where. So for x-intercepts, we had negative 6, and these grid lines are going by 2's, so here's negative 6. For the y-intercepts, we have negative 3, that's down here. For the vertical asymptote, we had x equals 2, so that's a vertical line going through 2. For the hole, we have 5, but we're not going to bother putting that on until we've actually drawn some of the graph that we can just figure out where 5 is on the graph. For the horizontal asymptote of y equals 1, that's a horizontal line going through 1 right here. And taking a look at this graph, I see that I've got plenty of information for graphing this to the left of this vertical asymptote. We've got these 2 points. Unfortunately, we don't know anything about what's going on to the right of the vertical asymptote. I don't know if I'm in the upper right or the lower right, so I'm going to need an additional point in order to figure out where I am and anchor this graph. For my additional point, I'm going to take an x value that's to the right of my vertical asymptote. Taking a look here, I'm thinking that 3 would help me out the most, and since 3 is not the location of a hole, I can use it in my simplified function here. So 3 plus 6 over 3 minus 2. Actually, let's go with 4. Just to be on the safe side, let's get a little bit further away and be on a grid line and go with 4. So 4 plus 6, 4 minus 2. So that's going to be 10 over 2, which is 5. So then I have the point 4, comma 5 right here. Okay, so let's go ahead and graph now. We have a branch that goes through these intercepts and approaches but does not touch the asymptotes on the left side here. We have another branch coming down across this asymptote, or at least near the asymptote, going through this point and going to the horizontal asymptote like so. And last but not least, we have this hole at x equals 5, which I'm going to put on the graph right there. There's x equals 5. So we're done with this one. For this function, I need to find intercepts, holes, and asymptotes and then graph it. Before I do that, it would be very helpful to factor this thing and see if there's any common factors that I can cancel out. So in my numerator, I notice I have a common factor of x that I can yank out of there, leaving me with x squared minus 4. And I can go a little bit further in the numerator. Since I have the difference of two squares, I can use my square root plus minus shortcut, split this up into x plus 2, x minus 2. Down below, I'm looking for numbers that multiply to negative 2 and add up to 1. That would be negative 1 and positive 2, so x minus 1, x plus 2. And I see that I can actually cancel out those x plus 2's. So there we go. That leaves me with x and x minus 2 in the numerator, x minus 1 in the denominator. Now that we've done that, let's go ahead and figure out our intercepts and asymptotes. For x-intercepts, those will be x values that zero out my simplified numerator. So x and x minus 2, setting that equal to 0 so that I can zero out the whole fraction. And I see that if x is 0 or 2, either of those numbers will zero out one factor and zero out the whole thing. So 0 and 2, then, are the x-intercepts. All right, for y-intercepts, we're going to plug 0 into the original function up here. So if I do that, I zero out the entire numerator, so that's 0. I zero out most of the denominator. I have a negative 2. 0 over negative 2 is just 0. And I guess we should be expecting that because we had an x-intercept of 0. That's right here on the origin, and that's also a y-intercept of 0. But hey, now we really feel good about that. Moving on to vertical asymptotes. These will be things that zero out the simplified denominator, make the simplified function undefined. So if we set x minus 1 equal to 0 and solve, we get x equals 1 for an asymptote. Next, for holes, those will be x values that zero out functions that are factors that got canceled out, things that would have made the original undefined but were removed so they don't make the simplified function undefined. So if we set x plus 2, the canceled out factor, equal to 0 and solve, we have a hole at x equals negative 2. For horizontal asymptotes, we have a top-heavy function, third degree versus second degree, numerator versus denominators, top-heavy. So there are no horizontal asymptotes. However, there is a slant asymptote that we can get if we divide the numerator by the denominator. And to make my life easier, because this would be a mess to divide with the original, I'm going to go with the simplified version here, and I'm going to distribute this out because that's the format I need it in. So I'll have x squared minus 2x divided by x minus 1. When I do that division, I'm going to get my slant asymptote. Since I'm dividing by a binomial, I'm going to need to use synthetic division. So let me set up my coefficients. So for my numerator here, I have a 1 for the x squared, a negative 2 for the x, and a 0 to hold the place of the constant that would be there, but there is no constant. For my box number, I'm going to use 1 because that's what zeroes out my factor of x minus 1. Bringing down that first one, we have 1 times 1 is 1, plus negative 2 is negative 1. And this is all we need, but we can keep going. 1 times negative 1 is negative 1, plus 0 is negative 1. We don't really care about the remainder. It's just the quotient that gives us our slant asymptote. So we end up with y equals 1x minus 1. And this is hopefully everything we need to graph this. We still might need additional points after we put everything on there, but let's go ahead and see. So let's start with the x-intercepts, 0 and 2. So here's 0. Here's the x-intercept 2. Next, the y-intercept, that doesn't give us anything new. We had a y-intercept of 0. Already got that for the x-intercept. For vertical asymptotes, we had x equals 1, vertical line going through 1. And I see right away that I have points on either side of my vertical asymptote, which means I'm probably not going to need additional points. This is probably going to be everything I need, along with the slant I'm about to draw to graph this thing out. So my slant asymptote, we had x minus 1, so that's a line with a y-intercept of negative 1, and a slope of up 1 over 1, up 1 over 1, like so. And let me draw my branches now. So we have one branch on the left here, hugging the asymptotes and going through that x-intercept. We have another branch on the right, approaching the asymptotes and not touching them, though, and then going through that other x-intercept. And one thing we don't want to forget about is this hole at x equals -2. So now that I see what my graph is doing at -2, it's down here, I'm just going to put the hole right on the graph there. So it's usually easiest to wait until you've got the graph graphed out and then just kind of stick the hole on after you have that. To graph and write the inequality here in interval notation, I first need to get the critical values, which for this polynomial here, there's no discontinuity, so we're really just talking about the roots or zeros, the things that make this equal 0. So to do that, I need to factor this. So let me start with taking out some common factors if I can. It looks like I can take an x out of all three terms, and also they're all divisible by 5. So 5x coming on out of there. That leaves me with x squared. This will be a 4x, and let's see, 60 divided by 5, I think that's 12, so minus 12. I can factor the stuff inside a little bit more. I need numbers that multiply to -12 and add up to +4. -2 and +6 would do it for me. So I still have my 5x, don't want to lose that. I also have an x minus 2 and an x plus 6. Now I'm going to go through and zero out each of these three factors to get my roots. So this 5x, if I plug 0 in for x, that makes 5x 0. For my parentheses here, 2 minus 2 would give me 0, so 2 is another root. And then this last one will have a -6 for a root. All right, now I'm going to go put these on a number line and do some sign analysis around them to see what kinds of numbers make this thing positive or negative. So here's my number line. For my dots that I'm going to use, since my inequality does not have any equals in it, I'm going to use open dots for all of these. So the furthest one to the left is -6 over here. We've got 0. We've also got 2. Doesn't have to be drawn to scale here. We're just kind of sketching this and getting the lay of the land. Now let me test something over to the left of -6, like -7. Plugging that in, 5 times -7 is negative. -7 minus 2 is negative. -7 plus 6 is negative. 3 negatives, odd number of negatives, giving me a negative result overall. Now I'll test a number between -6 and 0, like -5. So we're going to have a negative, another negative, and the only positive is -5 plus 6. So we have 2 negatives. That's going to give me a positive result. Now between 0 and 2, let me try out 1. 5 times 1 is positive, minus 2 is negative, plus 1 is going to be a positive. We only have a single negative, the x minus 2, so that whole thing comes out negative. And finally, a number bigger than 2, let me try 3. 5 times 3 is positive, 3 minus 2 is negative, positive actually, 3 plus 6 positive. They're all positive, so that's a positive result. Looking at my inequality, we said greater than 0, so I want all the positive intervals. So that'll be this second interval and this fourth interval. Now writing those in interval notation for this first one, I've got -6, 0, using parentheses instead of brackets because I've got open dots here. And then I need a union, and I have a 2, infinity, also with open dots, so also going to be parentheses, and infinity always gets a parentheses. On this problem, I want to graph and write out the intervals on which this rational function is less than or equal to 0. To do that, I need to first find the critical values and do a little sign analysis around those on a number line. So for critical values, those are going to be roots and discontinuities. Roots make the numerator only 0, and discontinuities make the denominator 0. So since this is already nice and factored out, I can just go straight to figuring out x values that zero out these different factors. I'll start with the discontinuities. So if I plug a -1 in for x, that'll zero out my denominator here. And for my numerator, my roots, I'm going to have x equals 7 for this first one, and 3 for this other one. Let me go ahead and stick those on a number line now. So the furthest one to the left is going to be this -1. Since that's a discontinuity, we automatically use an open dot for that. Next, I have a 3. Since that is a root, and since I have an equals for my inequality, I have to use a solid dot for 3, and for the other root as well for 7. Now I'll go through and test a number from each interval. So to the left of -1, I'll use -2. -2 minus 7 comes out negative. -2 minus 3 is negative. -2 plus 1 is also negative. 3 negatives, odd number of negatives, gives me a negative. Next, a number between -1 and 3. Let me use 0. That's pretty easy. 0 minus 7, 0 minus 3, those are both negative. 0 plus 1 is positive. We have two negatives. Even number of negatives comes out positive. Next, between 3 and 7, I'll use 4. 4 minus 7 is negative. The other ones all come out positive. 4 minus 3, 4 plus 1. We just have a single negative. So that whole thing is going to come out negative. Finally, bigger number than 7. Let's try 8. 8 minus 7, 8 minus 3, 8 plus 1. They all come out positive. So positive result there. Okay, so let me go through now and see which intervals I need. My inequality said less than 0. So that means I want the negatives. Less than 0 means negative. So that's this first interval and this third one. Writing all that in interval notation for this first interval, I can say negative infinity, comma, negative 1. And I'll use parentheses for both of those. Infinity always gets parentheses, and negative 1 is an open dot. Now I need a union, and my other interval, we're going to have 3 comma 7, and those are both going to be brackets because I had solid dots. So I have to show that those are actually part of the solution.